Have you ever wondered how real-time systems work in operating systems? These are computing systems that respond to external events or stimuli within set time constraints or deadlines. They're designed to provide timely and predictable responses to inputs, ensuring that critical tasks are completed within predetermined time limits. Real-time systems are integral to industries where timing correctness is crucial. Think about industrial control systems, embedded systems, automotive systems, medical devices, and even aerospace systems. They all rely on real-time systems to function effectively and safely. In essence, these systems are the unsung heroes, working behind the scenes to keep our world running smoothly. From ensuring your car's airbag deploys in a split second during a collision, to maintaining the intricate timings of a satellite in orbit, real-time systems play a pivotal role. Now that you know what real-time systems are, let's delve into their different types. Imagine a system where meeting deadlines is a matter of life and death. That's exactly what hard real-time systems are all about. Delving into the realm of hard real-time systems, we encounter a landscape where timing is everything. These systems function under the premise that certain tasks must be completed within a specified deadline. No excuses, no exceptions. The consequences of missing a deadline can be dire. Think system failures, safety hazards, or even catastrophic events. Operating systems designed for hard real-time systems are built with this urgency in mind. They employ deterministic scheduling algorithms and resource allocation mechanisms to ensure that critical tasks are executed within their deadlines. It's like having a strict, precise conductor leading an orchestra, ensuring that every note is hit exactly when it should be. These systems are commonly found in industries where timing is critical. Consider an air traffic control system where a delay of a few seconds could result in a mid-air collision. Or a medical device like a pacemaker, where a delay in electrical signal could prove fatal. In these scenarios, the hard real-time system ensures that the necessary tasks are completed within the predetermined time limits. In essence, hard real-time systems are the epitome of precision and reliability. They operate under the principle that every microsecond counts, ensuring that tasks are completed not only accurately, but also timely. So you can see that hard real-time systems demand strict adherence to deadlines. Not all real-time systems are as stringent as hard real-time systems. Enter soft real-time systems. In the world of computing, soft real-time systems make up a fascinating category. They're a bit like the more relaxed sibling to the hard real-time systems we've just discussed, while they share a family resemblance in that they both value the timely execution of tasks. Soft real-time systems are a bit more laid back when it comes to meeting deadlines. Now, that's not to say they're slacking off. Quite the contrary. Soft real-time systems strive to complete tasks within their designated deadlines. However, the key difference lies in their approach to missed deadlines. Unlike hard real-time systems, where a missed deadline might spell disaster, soft real-time systems are more forgiving. An occasional delay won't necessarily cause a catastrophic system failure or compromise safety. Let's imagine a multimedia application for a moment. If a video frame arrives a fraction of a second late, it might cause a minor glitch in the playback, but it won't bring the whole system crashing down. That's the beauty of soft real-time systems. They're designed to maintain overall system performance and responsiveness, even if it means occasionally missing a deadline. Operating systems for these systems prioritize maximizing the likelihood of meeting deadlines whilst ensuring good overall performance. They strike a balance between timeliness and efficiency, which is crucial in many applications. So while soft real-time systems aim to meet deadlines, they offer more flexibility than their hard counterparts. Now let's talk about the operating systems that support these real-time systems. The real-time operating systems, or RTOS. Real-time operating systems are designed specifically to meet the stringent requirements of real-time applications. They are the brains behind the operation, ensuring that tasks are completed within their deadlines and that the system responds promptly to external events. At the core of an RTOS is task scheduling. This is a process that determines the order in which tasks are executed. It's like a conductor leading an orchestra, ensuring each instrument plays at the right time to create a harmonious symphony. In an RTOS, task scheduling algorithms, such as rate monotonic scheduling, earliest deadline first, and fixed priority preemptive scheduling, prioritize tasks based on their deadlines and importance. This ensures that critical tasks are given precedence and deadlines are met efficiently. Another vital function of an RTOS is interrupt handling. In the digital world, interrupts are urgent signals that demand immediate attention. They could be triggered by various external events, such as sensor input or a hardware change. An RTOS handles these interrupts in a timely and deterministic manner, meaning it responds promptly and predictably to these urgent signals. Resource management is another essential feature of an RTOS. Just like a skilled project manager, an RTOS allocates system resources such as CPU time, memory, and I/O devices. This ensures that critical tasks have the resources they need to meet their deadlines. The RTOS does this while maintaining fairness and efficiency in resource utilization. A key characteristic of an RTOS is its emphasis on predictability and determinism. It's like a reliable friend who always arrives on time. An RTOS minimizes unpredictable delays and contention for resources, ensuring that task execution times remain bounded and predictable. Examples of real-time operating systems include VxWorks, QNX, FreeRTOS, and Arti Linux. Each of these systems brings a unique set of features and strengths to the table, making them suitable for various real-time applications. As you can see, RTOS is specially designed to support real-time computing requirements. Ever wondered how tasks are prioritized in real-time systems? Let's talk about task scheduling. This is the process where the system determines which task should be executed at any given moment based on certain parameters. It's the heart of any real-time system, as it ensures that time-critical tasks are executed within their deadlines. In real-time systems, scheduling algorithms are the magic behind the scene. They decide which tasks get priority and when they should be executed, based on their deadlines and criticality. Commonly used scheduling algorithms include rate monotonic scheduling, earliest deadline first, and fixed priority preemptive scheduling. Rate monotonic scheduling, or RMS, assigns priority based on task frequency. The more frequent a task is, the higher its priority. It's simple and efficient, but it's only suitable for periodic or cyclic tasks. On the other hand, earliest deadline first, or EDF, prioritizes tasks with the earliest deadlines. This makes it highly dynamic and more flexible than RMS, but it also requires more computational resources. Lastly, fixed priority preemptive scheduling assigns a fixed priority to each task. If a higher priority task becomes ready, it preempts the currently running task, ensuring that the most critical tasks are always executed first. These algorithms are just the tip of the iceberg. There are many more, each with its strengths and weaknesses, and each suited to different kinds of real-time systems. So task scheduling plays a crucial role in ensuring that critical tasks are executed on time. Predictability and determinism are essential in real-time systems. But what do these terms mean? Let's break it down. Predictability refers to the ability to accurately foresee the behavior of a system in response to a particular input or under specific conditions. For instance, if we press a particular button on a machine, we expect a certain action to take place. The consistency of the system's response to the same input is its predictability. On the other hand, determinism is the principle that every event, including the decision-making process of a real-time system, is determined by previously existing causes. In other words, given a certain set of initial conditions, a deterministic system will always produce the same output. Why are these concepts so important in real-time systems? Well, real-time systems operate in environments where timely and reliable responses are crucial. For example, in an automated factory line, if a robotic arm doesn't move exactly when it's supposed to, it can create a domino effect of delays, leading to inefficiency and potential losses. Or consider an airbag system in a car. If it doesn't deploy at the precise moment of impact, it fails its primary function of saving lives. Predictability and determinism in real-time systems are achieved by minimizing sources of non-determinism, such as unpredictable delays or contention for resources. For example, real-time operating systems employ deterministic task scheduling and priority-based interrupt handling. They ensure that critical tasks are executed within their deadlines, and high-priority interrupts are handled promptly, reducing the chances of unpredictable behavior. In essence, predictability ensures that a system behaves in a consistent manner, delivering the same output for the same input, while determinism guarantees that the system's behavior is reproducible over time, regardless of the number of times the process is repeated. These two principles serve as the bedrock of real-time systems, enabling them to function reliably within their operating environments. They are instrumental in ensuring that critical tasks are completed within their deadlines, and system responses align with the expectations set during the design phase. So, predictability and determinism help ensure that the system behavior is consistent and reproducible, which is key in real-time systems.